Section: Introduction. In this section, we discuss recent advancements in reasoning models, particularly those from OpenAI and DeepSeek, which have significantly improved the performance of large language models, LLMs, on complex tasks through techniques like chain of thought, COT. This method encourages models to tackle problems step by step, similar to how humans reason. However, this approach requires a lot of computational power during inference, resulting in lengthy outputs and increased latency. In contrast, we humans often use concise notes or drafts to capture key ideas without unnecessary detail. To address this, we introduce chain of draft, COD, a new prompting strategy that aligns more closely with human reasoning by emphasizing efficiency and minimalism. Instead of generating verbose intermediate steps, COD encourages LLMs to produce concise outputs filled with essential information at each stage. This not only reduces latency and computational costs but also maintains accuracy, making LLMs more suitable for real-world applications where efficiency is crucial. Our intuition behind COD is based on how we externalize our thoughts. When we face complex tasks, like solving math problems or writing essays, we typically note only the critical information needed to move forward. By mimicking this behavior, LLMs can focus on finding solutions without the burden of excessive reasoning. To test the effectiveness of COD, we conducted experiments across various benchmarks that require multi-step reasoning, such as arithmetic and common sense reasoning. Our findings show that this minimalist approach can maintain or even enhance accuracy compared to the standard chain of thought, while significantly cutting down on token usage and latency. The contributions of our paper are threefold. We present chain of draft as a concise reasoning strategy inspired by human cognitive processes. We empirically demonstrate that COD can significantly lower latency and costs without losing accuracy, and we discuss the implications of COD for the design, deployment, and usability of LLMs. In the related work section, we note that various reasoning language models have recently emerged, including those from OpenAI and Alibaba, which have shown improvements in handling complex tasks. These models utilize structured reasoning methods to enhance their problem-solving abilities. The chain of thought reasoning established a foundational approach, and more advanced structures like tree and graph topologies have been developed to tackle even more complex issues. While structured reasoning improves LLM's capabilities, it also increases token usage, making it less practical in cost-sensitive and time-sensitive situations. Some techniques, like streaming, aim to reduce perceived latency by providing partial outputs incrementally, but they don't fully address overall latency or computational costs. Other methods, like skeleton of thought, help lower latency but don't reduce computational costs effectively. Our approach, COD, can complement existing methods to further decrease latency. Other works, like Coconut, attempt to reason in a continuous latent space, which can lower latency but may sacrifice accuracy and interpretability. The closest approaches to ours are concise thoughts and token-aware LLM reasoning, which propose fixed or dynamic global tokens for reasoning steps. However, these methods can be impractical and may not adapt well to varying task complexities. In contrast, our approach uses a per-step token system, allowing for unlimited reasoning steps and greater adaptability to different structured reasoning techniques. Section Summary. In this section, we introduce chain of draft, COD, a new prompting strategy for large language models that emphasizes concise reasoning to enhance efficiency and reduce latency while maintaining accuracy. We also discuss related advancements in structured reasoning frameworks and highlight the limitations of existing methods, positioning COD as a more adaptable solution for real-world applications. Section: Chain of Draft Prompting. In this section, we introduce the chain of draft, COD, prompting strategy, which builds on the chain of thought, COT, approach. While COT has proven effective for tasks requiring complex reasoning, we notice that large language models, LLMs, often generate overly detailed reasoning steps, using many tokens before reaching an answer. In contrast, we observe that humans typically take a more concise approach, focusing on essential intermediate results rather than elaborating on every detail. Inspired by this, we propose COD, which aims to minimize verbosity by limiting the number of words in each reasoning step to only what is necessary for calculations or transformations. To illustrate the differences among standard prompting, COT, and COD, we consider a simple arithmetic problem about Jason and his lollipops. In standard prompting, the model might simply provide the answer without showing any reasoning, which can lead to a lack of transparency. COT, however, offers a detailed reasoning process but often includes irrelevant information, increasing the token count and response time. In contrast, COD distills the reasoning into concise equations, focusing solely on the necessary mathematical operations, thus reducing token usage while maintaining clarity and correctness. For our experiments, we follow the original COT paper and evaluate 3 categories of tasks: arithmetic reasoning, common sense reasoning, and symbolic reasoning. We select tasks where COT significantly enhances accuracy compared to a baseline. Our experimental setup compares 3 prompting strategies: standard, COT, and COD. In standard prompting, we provide input-output pairs for the model to follow without reasoning. For COT, we use examples from the COT paper but format the final answer for easier extraction. In COD, we encourage the model to think step by step while limiting each reasoning step to 5 words as a guideline, not a strict rule. We also include manually created COD examples for reference. We evaluate each task using 2 leading models, GPT-4o from OpenAI and Claude 3.5 Sonnet from Anthropic. Section Summary. In this section, we introduce the chain of draft, COD, prompting strategy, which aims to enhance reasoning efficiency in large language models by condensing multi-step reasoning into minimal, essential steps, thereby reducing verbosity and token usage. We compare COD with standard and chain-of-thought prompting through empirical experiments across various reasoning tasks, demonstrating its effectiveness in maintaining clarity while minimizing unnecessary details. Section: Arithmetic Reasoning. In this section, we first examine math problems that assess the arithmetic reasoning abilities of language models. We find that GSM-8K is the preferred benchmark for this purpose, offering a dataset of 8,500 varied grade school-level math problems, each accompanied by a detailed solution that highlights skills in arithmetic, geometry, algebra, and logical reasoning. Our evaluation results indicate that both GPT-4o and Claude 3.5 Sonnet face significant challenges with standard prompting, achieving accuracies of 53.3% and 64.6%, respectively. However, when we apply the chain of thought, COT, method, both models exceed 95% accuracy, though this requires generating around 200 tokens per response. In contrast, the chain of draft, COD, approach yields an accuracy of 91% while only needing about 40 tokens per response, which reduces the average token count by 80% and decreases latency by 76.2% and 48.4%, respectively. Next, we evaluate tasks related to date understanding and sports understanding from the Big Bench dataset to showcase the effectiveness of COD in common sense reasoning. We maintain consistency by using the same system prompts as in the arithmetic reasoning evaluation. Our results reveal that COD significantly lowers latency and costs by producing far fewer tokens in responses compared to COT. Additionally, COD often outperforms COT in accuracy. Notably, for the sports understanding task, COT generates overly lengthy responses for Claude 3.5 Sonnet, while COD reduces the average output tokens from 189.4 to 14.3, marking a 92.4% decrease. Lastly, we explore symbolic reasoning through a coin flipping task, where language models predict the outcome after a series of coin flips. Since the original dataset is unavailable, we create a test set of 250 examples based on the same design. We randomly select 4 names from the top 1,000 first names in the US and decide randomly whether to flip a coin for each name. For instance, we might ask if the coin remains heads up after a series of flips. Our evaluation results show that GPT-4o and Claude 3.5 Sonnet achieve 73.2% and 85.2% accuracy with standard prompting, respectively. However, both models reach perfect accuracy with COT and COD, with COD significantly reducing token usage compared to COT, from 68% for GPT-4o to 86% for Claude 3.5 Sonnet.